All right, given our high quality technology equipment here at Springford Area School District, I'm going to continue on. I guess the video cut out because the battery died and I finally recharged it, and I guess I'm going to start talking about this here on the board, talk about cations, anions, and valence electrons. So let's take a look. Okay, here I am, I'm coming. All right, so overall I focused on the first, well, period 1, which is kind of up here, period 2, period 3, and a little bit of period 4. Okay? And we talked about periods go horizontally across, arranged by increasing atomic number. Groups or families go vertically down. They all are arranged because they have the same number of valence electrons, and they all tend to react the same way. So let's talk about each family. Okay? Here, group 1 are the most reactive metals. Okay? And over on the periodic table we said metals are the most reactive all the way to the left and decrease in reactivity as you go from left to right. That's the metallic trend. So over here I got the alkaline metals, and I'll write that up here for you guys. Somebody's asked about how to spell it. I'm going to put it right here. A-L-K-A-L-I metals. Alkaline metals are the most reactive family or group of metals on the periodic table. They have one valence electron, okay? So what they want to do is they want to lose a valence electron. They want to get rid of that valence electron very quick so they have a full outer shell. And the full outer shell they would show would be the following. So if I have lithium right here, 2 in the first level, right? 1 in the second, well, what's quicker? Gain 7, right? Or lose 1? Lose 1, because it's going to give it away to a nonmetal. This says bye-bye. Look what's left over. A full outer shell with a positive charge. Okay? So that's a cation. Positive charged ions. It's now an ion because it gave a valence electron away. Again, once that valence electron goes, it becomes an ion. So all these guys, all these atoms want to give away an electron, the valence electron, form a cation in an ionic compound. Then we have group 2. They are called the alkaline earth metals. I'll write it right here so you can see. A-L-K-A-L-I-N-E, earth metals. Alkaline earth metals. A-L-K-A-L-I-N-E, earth metals. They have 2 valence electrons. They're the second most set of reactive metals on the periodic table. Located in group 2. What do they want to do? They want to give away or lose 2 valence electrons. And once they get rid of them, once that once that valence electron goes, it becomes an ion. Once it's gone, it becomes an ion. So I'll draw a small little beryllium right here with an atomic number of 4, 2 protons and 2 electrons in the first, 2 in the second. So what's easier? Lose 2 or gain 6? This is going to want to lose 2. So it happens rather quickly. Not as crazily or as quickly as alkaline metals, but rather quick. So these guys lose 2, and once they become ions, they end up with a positive charge. So another set of cations, positive 2 charge. Then we start to look into the zigzag, as you saw over on the periodic table. The zigzag is a borderline that separates metals from nonmetals. And we also talked about transition metals. Okay, hopefully I talked about that in the last part of the video, but just in case. Transition metals from groups 3 through 12, they tend to rust when they react. Not violently explode and go crazy. Okay? And we had the song from Kansas. And here's my copyright, or bibliography. Kansas, it's a group. They sang a song called Dust in the Wind. Download it. It's a wonderful song. Kansas is located in the middle of the country. Transition metals are located in the middle of the periodic table. They had a song called Dust in the Wind. All we are is dust in the wind. Well, my song is transition metals. Rust in the wind. Isn't wind air? Movement of air. All we are is rust in the wind. So instead of violently exploding like an alkaline metal or reacting vigorously like an alkaline earth metal, they tend to tarnish or rust. That's the way they react. And when they tarnish or rust in the presence of air with water as a catalyst, they form a metal oxide. We'll talk about that later in the following chapter. So they rust. Then as we go to past the zigzag, on the zigzag, we got metalloids. We also have the boron family. They are still cations because they want to get rid of 1, 2, 3 valence electrons to become stable. and they have a positive 3 charge. Once they lose them, once they get rid of them, give them to anion, they become stable. Then you got carbon and silicone. They share. Usually they are involved in molecular compounds or hydrogen bonding. They tend to share. These guys here, now we're on the other side, but mostly nonmetals. They have a charge of -3. Each of these guys in group 15, the nitrogen family, have 5 valence electrons. So they could lose 5 or gain 3. They're going to gain 3. And once they gain those 3 from the cations, you see they go hand in hand, anionic compounds, they become stable. Now, these are all nonmetals. As we go from left to right from the zigzag, reactivity increases. So these are pretty reactive. Oxygen family is even more reactive because they're only 2 away from becoming stable, because they have 6. So all they need is 2 more, and they're stable. So they're pretty reactive. So they gain 2 anions, a negative ion, and a -2 charge. Group 16, 6 valence electrons. And here we go. Halogens, nuts, freaks, most reactive nonmetals. Why? Because they're only 1 away from becoming stable. The alkaline metals are 1 away by giving 1 away. These guys take that 1. And they're the most reactive nonmetals. They gain 1 valence
Make sure we have everybody checks
Hi,
their
Mr. Stiggins. I'm
posters,
trying to
either
film.
taken down or they're covered before you leave today.
I'm still
I'd
teaching.
appreciate that.
Thank you.
Once again, scientific calculators, thank you.
Scientific calculators, that's right. Here we go. Okay. Integrity on the PSSA. All right, so you have the halogens. They gain 1 valence electron. They're 1 away from becoming stable. So the trend of metals, reactivity decreases from left to right up to the zigzag. Non-metals, reactivity increases up to group 17, where they're the most reactive. And then the noble gases have that full outer shell. Okay? They have that full outer shell. They are inert. They do not react. They all go together, except for helium, the little crazy one. Well, he's inert, but he's got 2 valence electrons. But as we learned in class, 2 for helium is the full outer shell, because that's what the first level holds, 2. The rest of them have 8, and they have a full outer shell. Okay? So that's the overall trend of reactivity. Talk about the difference between metals and nonmetals real quick. I'll talk it through so you guys see it, so we can have more time next week to focus on extra enrichment. All right, so we're going to push this over here. Take a look at that. Okay? Properties of metals and nonmetals, really important. These you just pretty much have to memorize. Metals tend to form cations because they want to give away a valence electron. They tend to be shiny, hard, and lustrous. Lustrous and shiny go hand in hand. Okay? Here's my ring, wedding ring. Here we go, I'm going to drop it. Watch this. Hopefully this works. Whoop! Hold on, I can bounce it even higher. Didn't make it then. Oh! How come I can do this in class and I can't do it on live film? Here we go. Let's try it again. You can see I don't edit things out. Whoop! One more. Why is it not bouncing right? Oh well, whatever. Metals, shiny, hard, lustrous. They are good conductors of electricity. And we'll talk about metallic bonding and a little bit of valence electrons later on. Because of that, they tend to have a low specific heat. Because remember, substances that can have heat and energy pass through them rather quickly, movement, right, tend to have a low specific heat. They do not require much energy to heat up, and hence don't require much energy to leave to cool down. Okay? Ductile. Oh, I'm sorry, I skipped malleable. Malleable. Ever hear of a hammer named like a mallet? Well, metals can be shaped. Malleable means shaped into different shapes, pounded into different shapes. I always associate mallet. Picture me with a mallet, bam, 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 pounding metal into a different shape. It can be easily shaped. Some metals are softer than others, but overall they are pretty hard. Ductile metals can be drawn out into a wire. Ductile, drawn into a wire. And they also have a high melting point and tend to be solids at room temperature. Except for mercury, Hg realms of mercury, that's a liquid room temperature. Nonmetals tend to be the opposite. Metals are shiny, hard, lustrous. Nonmetals, dull and brittle. Brittle means break easily. Metals, good conductors of heat and electricity. Low specific heat, don't need much heat to heat up, don't need much heat to leave to cool down. These guys take forever to heat up, and take forever to cool down, higher specific heat. And they can also be found as solids, liquids, or gases at room temperature. And as you notice over on the periodic table, you'll see I'll turn it over there, because again, we're a one-man camera crew here. Hold on. Let me zoom out. Wrong button. Red, gas at room temperature. Blue, liquid at room temperature. You see bromine there. And HG rhymes with mercury. Right down there, you see mercury right there. Yeah. And the rest, black, are solids at room temperature. So let me talk through this one more time. There are the alkaline metals group 1, alkaline earth metals group 2, transition metals, rust in the wind. All we are is rust in the wind. Some metals up to the zigzag from left to right, decrease in reactivity. Then you've got the metalloids, which show properties of both metals and nonmetals. We'll get to that next week. And then we start the nonmetals. And you see the nitrogen family, N, oxygen family, O, F, fluorine family, my gosh, halogens. Those families increase in reactivity from left to right until you get to the snobs, the noble gases, who already have that full outer shell. They don't need to react. Okay? And again, looking at the outline, I'm trying to see if there's anything else I can cover at this point. Mendeleev, old mass, mom, modern atomic, number new. I think we've covered a lot here. This will take forever to download. We'll talk about metalloids in class. We'll talk about atomic radius, shielding effect, ionization energy, electronegativity, electron configuration, electron affinity next week. We pretty much hit everything else. So we're in good shape. All right. So there you go. There's your chemistry. So now you have PSSAs coming up for 2013 and 2014 next week. If I'm using this next year, who knows when I'll do this. But anyway, work hard, step it up. This is for you. So we have shortened classes. This will help you study. This will be your tutoring. And we'll spend our 30-minute periods doing the higher level stuff to make sure we're good. And we should be ready for our test the following Monday. All right, over and out. Bye.